Next, we have Paula Kimmerling, who will be presenting on average mixing matrices of continuous quantum walks.
Hello, my name is Paula. I'm going to talk to you about the average mixing matrices of continuous quantum walks. So, it is a fact that if I give you a graph, which is what this thing is over here, it's got nodes and edges connecting them, I can create what's called an adjacency matrix, which is this first matrix over here, named A. If two nodes share an edge, I put a 1, and if two nodes do not share an edge, I put a 0. So that doesn't tell me much about what a continuous quantum walk is, but imagine you're playing Twister on the graph. So your body parts are spread over the different nodes, and you can only move them in the directions of the edges. Where you start is what I'm going to call my initial matrix D. How I move along the graph is what I'm going to call this transition matrix, U of t. It is time dependent. It is based on the adjacency matrix. I am going to move around my graph by this first equation, U of t, d, U of negative t. This is a quantum walk. This equation is a quantum walk. There's not a lot more to it. It's a very mathematical object. What can I do with this? I can study the U of t, U of negative t. I can see what my transition matrix is forcing me to do when I'm moving around the graph. And in particular, I want to know what happens over the long term. So I'm going to take a time average. And this is going to be my m hat. M hat, which is the second matrix I have up there for this graph, is the average mixing matrix. It's how I'm going to move around the graph. If I ran it 1,000 times, on average, that's what it's going to do. This is related to quantum computing. So I can study properties of A and m hat, and with them, I can create different types of quantum gates and different types of quantum algorithms. So if I can study these and get meaningful classification properties, I can start to classify different types of quantum walks, and I can start to classify different types of algorithms and try to find algorithms that work well, which is currently the problem with quantum computing. We need algorithms that run really, really well, because we can't have very many qubits. And that's my talk. Thank you.